Welcome back to the classroom. This is Mr. Wong. Today we're going to be covering Module 8, Applying Chemical Ideas. We're going to be investigating Inquiry Question 2, Analysis of Organic Substances, with particular focus on this following dot point. So we're going to investigate the processes to analyze the structure of organic compounds, specifically mass spectrometry. Alright, just for your reference, textbook values there. What we're going to be trying to look at is describe the function of mass spectrometry, and we're going to try and learn to interpret the mass spectra diagrams and look at all the different types of fragmentations and molecules we're trying to observe. Okay, so let's just quickly talk about what analytical techniques are. Okay, so analytical techniques are quite useful to understand the way in which matter is structured, and we're using light to help us work out the structure of different types of really tiny molecules. So as you can see here, sort of gives you a rough idea of the wavelengths of each types of models. So you can see whatever we can see here is what we call within our visible spectra. Basically all colors of light is in our visible spectra. That's what we see, the different colors. However, the light that we see is called visible light. Anything on the other side of that spectra, you have infrared, microwaves, radio waves, all those are things we can't physically see because our eyes cannot register those particular wavelengths of light. However, we can manufacture and use these types of lights, which by the way also is just radiation. We can use these different wavelengths of light to help us look at the different structures of really tiny molecules. So we can use that. We can use electron microscopes to help us look at bacteria, really microscopic things. We can use X-ray diffraction to work out the structure of a crystal. So they have many uses and purposes. Before we go on, just a little bit of physics implemented here, but what is electromagnetic waves? So everything you see here, any form of light, UV, visible, they are all electromagnetic waves. Now the idea is an electromagnetic wave is an oscillation of electric and magnetic fields acting perpendicular to each other. So you can see it vibrating like so. There is no physical, so what we mean by no physical vibrations, it doesn't need to interact with any particles, any form of matter to continue its motion. All you need is an oscillating charge to begin it, and you have this electromagnetic wave. Now there are many different kinds, and that's what we call the electromagnetic spectra. Light is essentially electromagnetic wave, or at least the light I'm referring to is visible light. And you have all these different other types going along like so. Depending on the wavelength you use, you can look at a lot of different types of structures. The shorter the wavelength, the smaller type of molecule structure we can look into as well. The first person to actually propose how electromagnetic waves are produced and propagate is this guy called James Maxwell. So that's just kind of showing you how if a charge is oscillating, you generate these electric fields and magnetic fields. So just kind of giving you an idea of what we're trying to deal with light. The other important factor is, as we said, light has a lot of different types of wavelengths. And when I refer to light, I do mean the electromagnetic spectra. With the spectra, we have different types of wavelengths, and you can see it gives you different types of analysis. So if we use infrared radiation, that can actually tell us the type of motion or the type of bonding that's occurring in a molecule. We can use ultraviolet light to look at single bonds, double bond systems. We can use X-rays to look at the structure, the three-dimensional structure of crystals. Remember, one of the most important applications we've used X-rays for is to do the photo 51, the double helix model for Rosalind Franklin. So you can see how the implications of these analysis techniques have helped us understand a lot more about the world we live in. So the one we're going to talk about today is mass spectrometry. And as you can see here, there's a really simple structure. These three images really kind of illustrates what's happening in mass spectrometry. In this here, we actually don't use any type of light to try and cause these images here. We go back to a more fundamental thing. We actually try and use electric fields and really strong magnetic fields to separate components of a molecule. So that's kind of why you see it sort of separates into a detector. And that's why you see sort of these really fine splittings of lines showing the different concentrations. So we're going to talk about the structure of mass spectrometry first, just so you get an idea of how it works. So how that allows us to see something like this. And then we're going to try and learn to interpret the graph here and work out what we're trying to do. Okay, so let's get started. Alright, so firstly, just to go on to the idea of what is mass spectrometry. Now this is the one and only one that we talk about that doesn't use electromagnetic radiation. So technically it's not a spectroscopic technique. However, it does help us work out the molecular mass of whatever molecule we're looking at. And it also tells us the molecular structure. Okay, so we're going to look at how we can work out the molecular mass and the molecular structure just by interpreting these kind of charts. Okay, just a bit of background information of how the mass spectrometer works. So in the laws of physics, we know that if we have a current carrying wire, so some kind of conductor connected to a circuit, if it has an electric current going through it, it's going to experience, or it's going to induce, a magnetic field. Okay, so if you actually look at this little GIF that I've made here, this is actually called the motor effect. So this is a really thin piece of aluminium foil, and it's running through electric current. And this electric current has its own magnetic field. You can see when I put two magnets of opposite polarities near this string, or near this aluminium foil, the aluminium foil is vibrating in both directions. So what's actually happening is the magnetic field of the two magnets is interacting with the magnetic field of the aluminium foil. So there's a force of attraction and repulsion occurring, and that's why you see this vibration occurring here as well. Okay, now mass spectrometry works in a really sensitive values, so just remember, you know, your units of substitution. Obviously we are dealing with very small values, so make sure you know which one's which, what we're representing. But we're more focused on obviously the actual interpretation of diagrams or of the graphs, and also how the actual technique works. Okay, so there's 5 stages of mass spectrometry. Okay, the first step, and we'll wait for the animation to start back. The first step is ionization, acceleration. Second step, deflection. Third step, detection, and deflection again. Okay, so 5 very key points of how this mass spectrometry works. So let's break it down into these 5 steps and look at what's happening. Okay, so the first part is ionization. Okay, so this is the structure of a mass spectrometer. You can actually see it's quite similar to the setup they make for cathode ray tubes. So what's actually happening here, we have an electron gun. So this is what we have here. So we have the electron gun here. We inject on one end the sample of whatever organic molecule we want. Okay, so that organic molecule is going to go through here. You can see in the diagram here it says a heater vaporized sample. So the idea is we want to vaporize the sample, so we want to make it into a gaseous form. The reason why we want it in a gaseous form, if you remember the 3 simple states of matter, solid, liquid, and gases, after the gas stage, we have the plasma stage. Now the plasma stage just means the molecules are broken up into ionized components. So the electron gun here is trying to cause the molecule to become ionized. Okay, so by forming these ions, we can later separate it with our electric fields and magnetic fields. So that's the function of our electron gun that we have here. Alright, just to break things apart, so imagine this is the molecule we have here. Okay, we have butane. Now let's have a look at how many components can this butane be broken into apart by. Because remember, the function of the ionization process is to firstly make this molecule into an ion component, and then that ion component can then also break into further smaller components as before. Now just to help you out here, typically single carbon-carbon bonds and single carbon-oxygen bonds will break very easily, whereas single carbon-hydrogen bonds and carbon double bonded to oxygen don't break very easily. So we can actually cause breakage in multiple areas. We can cause a breakage between these two bonds here. So I'll just highlight that. So it causes a breakage here. So we can get it like this. Or the breakage can occur here. So we get this whole molecule coming in this part here. Or we can break this part here to get a ionized component like so as well. Okay, so let's have a look at the different components we can generate. So the first one we have is this one here. As you can see, it's a very similar structure to what we have, but we've caused it to ionize, so we've displaced a electron. So this is the first step of the ionization process. We still maintain the molecular structure of the molecule that we put in, but we've converted it into an ion. What we call this is the molecular ion. If you actually look at the graphs later on, we also call it the molecular ion peak, or the parent ion peak, and essentially this will reveal to us the main molecular mass of the molecule. Okay, so maybe I'll just show you quickly what we mean by. Okay, so what we mean by the molecular ion, or the parent ion, you can see on this chart here, this very big peak here, or this large peak here, it's going to have the same molecular mass as the molecule used. The only difference is this is an ionized version of the molecule. So you can see the actual molecule we use in this chart here is the exact same formula here, barring we've lost one electron. Okay, so that's what we have. If we break it into its fragment ions, we can see here it could be a propanol group. Okay, so that's one fragment group. You can have an ethyl group, that's another component. We could have a methyl group. Okay, so those are the three different kind of components we can just break out through this butane molecule. So let's try and work out how everything comes together. Now again, like I said, the concept of mass spectra is to break things into fragments. That can actually tell us the structure of the molecule, and it can also tell us the molecular mass of that set molecule. Now remember, the electron gun is essentially going to use these electrons to ionize the molecule, so that's the function. So you can see if we had a helium atom, we injected an electron, we ionize the helium atom, and we can then break it into further fragments. So say for methane, CH4, can break into these particular components here. Okay, so that's what we're using with the electron gun. Alright, so the next bit is, why do we want to ionize these components? Because ionized charged particles will interact with electric fields and magnetic fields. Okay, we have these little electric fields here, you can see here. Once things are ionized, these electric fields will accelerate, obviously because of electrostatic force. You can see there's little holes in between here. So this allows the ionized molecule to, or fragments, to be accelerated through this slit. Okay, and so as it's moving really fast, this will allow the magnetic field to bend it in a particular direction or cause it to have a separate force. Just for those who are interested in the maths behind this, I'll just quickly put down the formula. So we know that the force exerted by a magnetic field is Q, so the charge of the fragment, times its velocity times the strength of the magnetic field. Okay, so the main thing that's going to separate how fast or how much bend is being caused onto these charges will in part be the velocity, or the velocity of these charged ions once it's been accelerated by the slits. Okay, how much bend does occur is partial related to the charge of the particle, or the ion, and their overall mass as well. Okay, so again, this is just the main process of the mass spectra. We have to have vaporization first. We need to make it into a gas. Once it's a gas, you can ionize it with the electron gun. So we can knock off one electron from the molecule to make it into a positive ion. This can allow it to break into fragments, which is then accelerated by the electric field. That's then deflected and altered, so it goes through a circular motion path you can see here under magnetic field, and then we can detect, based on the concentrations, the mass ions, the charge of the ions, and put it into separate components in terms of their mass and charge, and then we can compare in terms of their relative abundance. What you can also see here is the lighter the mass, the more deflection we'll see, and also similar ideas for the charge. So the more charge, more mass, the greater deflection we'll see here. Okay, so if you want to just try and remember the whole steps, you can remember as Victor is a daft duck. So there you go there. Alright, so that kind of gives us an idea of how mass spectrometry works. We are trying to work out the molecular structure, we are trying to work out the molecular mass. And this can be done by using ionization, it's through using electric fields, magnetic fields, to break it into fragments. Now how much deflection we get, remember, depends on the mass of the ion and the charge of the ion. If we combine these two factors, we actually call it the mass to charge ratio, and that's a really important part. We actually use this ratio as a component of the graph that we're going to be plotting as well. Alright, so that kind of just illustrates that very nicely. When they separate into different components from that magnetic field, or the magnetic field bending them in different magnitudes, that's going to cause them to scatter across a particular chart as the one you see here, and you'll see all these little tall lines shaped together. Okay, the highest concentration of fragments will obviously yield you the tallest chart, and you have the comparisons for others as well here. There can be a situation or scenario where there's too much bend, and so the charge to mass ratio is too small and it doesn't get detected, or at times it could be the charge to mass ratio or the ion is too large, and so it can't be bent at all. So there can be those kind of little instances, but those are few and far between. Okay, so the next thing we're going to do is actually interpret these types of printouts from a mass spectrometry. You have on the x-axis the mass to charge ratio, and over here you have the relative abundance. Okay, now based on where it is on the chart, so let's say this particular molecule here on this chart here, It will tell you what the charge to mass ratio is. You can also use this to help you work out what the overall atomic mass unit is of the molecule as well. Okay. So if we have a look at this diagram here, it nicely illustrates what we have. So looking at peak M-Z30, so the charge mass ratio of 31 here, you see that's the peak. Okay, so that's the peak concentration. We call this the base peak because this is where we have the most abundant fragment of the molecule ethanol. So this fragment that we have here, okay, that's the most abundant fragment after ethanol has been ionized and fragmented, or what we call fragmentation. You can see based on the relative intensity, this is 100%. So relative intensity is actually based on a comparison of the most abundant fragment you have. Okay? So all these values that we have here, these are essentially in comparison to how much there is of this most abundant fragment here. You can see with this chart here, so MZ46, so this value here, this is called the molecular ion peak. So as we said, this has the molecular mass of the compound or the molecule that you use in your investigation. So by looking at the peak, the far peak here, you can work out the molecular mass of the organic compound or molecule that you used. Now obviously no one expects you to remember or know for a fact what each specific line will tell you or what each specific fragment could be in terms of the structure. We actually know some really common ones in terms of common fragmentations. So these are all the values that you can find. Okay, so we know that M15 represents a methyl ion group. If we get a M17, that represents a hydroxyl ion group. So it's actually given to you. So you should be able to work out, or at least in under exam conditions, some information should be provided to you that allows you to actually look at these different mass to charge ratios and then interpret these graphs, what the exact structure could be. Okay, so like we said, the tallest peak is called your base peak. That's the most abundant fragment. The one furthest to the right, that's your ion or molecular ion peak, which basically tells you the molecular mass of your molecule. Okay, so that kind of tells you here. So remember, the x-axis is the charge to mass ratio. You can use that to help work out the molecular mass of the original compound you vaporized and then ionized. And then on the y-axis, it tells you the relative abundance of the different fragments you have of that particular molecule. And remember, every peak is plotted relative to the peak base, so the most abundant fragment that you have. Okay, so let's go into some questions and work out using this particular chart here, this mass spectra, or we'd like to call it. We have an unknown alkane, and we want to identify its overall molecular mass. We also want to know what type of alkane we have, and then we want to work out what the peaks are for 15, 28, 29, and 43 on this chart. Now, just to help you out, I've given you this chart here as well, the common fragments. So what you might want to do is just pause here and give yourself a bit of a chance to answer the question. Okay, so let's just go through this question. If I look at this, if I want to identify the alkane, I'll need to look at the molecular ion peak. So this is my peak here, so that's my molecular ion peak, and that's roughly about 44. Okay, so the mass of this, the molecular mass of this element or compound is 44. So if I do a little bit of deduction, remember this is an alkane. So an alkane's general formula is CnH2n plus 2. Okay? So obviously you'll need to know what specific formula you're dealing with as well. If we actually have a look, this would be actually propane. So C3H. Let's see, what do we have? 8. Okay. We know that carbon is 12, roughly 12 times 3 plus hydrogen, which is about 1 times 8. That equates us to a number very similar or very close to 44. Okay, so that is the structure that we have, or that is the alkane that we have. So that's propane here. The next one we're going to look at is the peaks at 15, 28, 29, and 43. So we can attribute, according to this chart, peak 15 is due to a methyl group. So it's due to 3. That's our methyl group. 28 here. We have our H2C double bond there. So that's, according to this, an ionized ethene. So our radical there. Or you could, what you could do as well, instead of doing the dot, you could just write that. So that and that would be the same thing. 29, we'll just wrote over myself. 29, it could potential, or 29 here would be an ethyl group, or ethyl group here. Okay, don't need the plus if you're going to do the dot, but you can do the plus either way. What you can see here though, on my chart, it has an aldehyde group, but obviously the question states that we're dealing with an alkane, so obviously that can't be an option there. And then the last one, 43, we have our other bond here. Okay, what you might want to do, you might even want to draw out the structure of the ion, but that wouldn't be really necessary here. So that's all the different peaks we have. You might want to say what the name is as well, but we see it's propane and it's broken into these fragmentations. Okay. Right, another question that they might ask of you besides interpreting the chart might be to work backwards. So they might give you the mass to charge ratio, and they might ask you to determine, using the mass to charge ratio, the molecular formula and the name of the particular substance you're dealing with here. So same idea what we did before. We're dealing with an alkane. So with an alkane, we know the structural formula, or the general formula, CnH2n2+, and we have a ratio, or a mass to charge ratio of 86. Okay, so the way in which we want to set this up is, we know, generally speaking, if we're talking about the general formula, we're looking at the number of carbons plus, in terms of the mass, plus the number of hydrogens, mass included. So that's what we have. So what we're going to do is we're going to sub in the atomic mass of carbon and hydrogen as its whole numbers, and then we can work it that way. So we know that the mass of carbon is 12, so 12n, because it's a fixed number we're looking at here, it's a integer. Hydrogen is 1, so 2n plus 2 equals 86. So you can just rearrange our equation here. So it'll be 14n plus 2 equals to, whoops, getting ahead of myself, 86. So 14n equals to 84. So put that onto your calculator. 484 divided by 14 gives you 6. Alkane we're dealing with has 6 carbons and 14 hydrogens, and so that is hexane. Okay, so that's how you deal with it. Alright, you might want to also try this past paper question. So using the mass spectra of butane, labeled here, identify and provide reasons for the 3 chemical formulas for the 3 peaks, X, Y, and Z. Now you will need to use the chart that I showed you early on before. You should be able to find it also on your data sheet, so please use those to help you work out this question. Marking criteria is here as well if you need. Okay. Anyhow, this is just a summary of what we talked about with mass spectra. Remember, you need to understand how the actual application of it works, so the setup, the 5 different steps, and also how to interpret the graphs. Okay, so hopefully you found this video useful. I'm going to end it here today. You're always welcome to replay or rewatch the different content. But again, once again, welcome back to the classroom. Thank you for joining in, and I'll see you next time.